Good morning to everyone. My name is Patrick Njomeni. I am a staff member at Northwest University. I will be the chair of these sessions. Our speakers of today is Dr. Mathew Aibinu. He is a postdoc fellow in the Institute for System Science at Durban University of Technology. And he obtained his PhD degree in mathematical science from the University of KwaZulu-Natal. And he has developed various iterative algorithms for finding the fixed points of several nonlinear problems. He's fascinated with solving optimization problems, and his present scope of research interest includes applications of differential equations. Today, he's going to talk about algorithms for equations of Hammerstein type and applications. Dr. Mathew, you have the floor.
Good morning, everyone. My name is Mathew Aibinu. I'm a postdoctoral fellow at Durban University of Technology. Today, I'll be talking on the topic titled Algorithm for Equations of Hammerstein Type and Applications. This will be the outline for the presentation. There will be a brief introduction, then preliminary will be given, and there will be a short literature review on what have been on existing results, and then the contribution to knowledge for this present study. And then we shall look at the application to the real life problem, and numerical example will then be given. Algorithms. Why talking about algorithms? According to Merriam-Webster, algorithm can be defined as a procedure for solving a mathematical problem in a definite number of steps that frequently involves repetition of an operation. What this one is simply means that what an algorithm is, that is, there will be repetition of operation, and the aim of using algorithm is for solving mathematical problems, and algorithm usually have a finite number of steps, and it involves repetition of operation. In computer science, algorithms are indispensable. In fact, an algorithm is important in optimizing a computer program. Literally, computer is just an empty box. For instance, if you put a data into a computer and it returns the results to you in an efficient way, it is due to an algorithm that a scientist or a mathematician has worked on. If you slot in, maybe you slot in a mathematical problem, maybe you say just 10 raised to power 2 raised to power 50, and it just gives the result. Literally, computer is just an empty box. It cannot give any. It cannot give any. It cannot do the computation on its own. But the outcome that will come out, it is due to an algorithm which has been worked on, which has been produced either by a scientist or by a mathematician. A best chosen algorithm will make the computer do a given task in an appropriate manner. In cases where efficiency matters, in fact, it is algorithm that needs to be used. There are different types of algorithm. However, that is not the focus of this presentation. Where we will be talking about the equation of Hammerstein type. Nonlinear integral equation of Hammerstein type defined on omega have the form given by equation 1.1, where in equation 1.1, omega is a measure space and y stands for a sigma finite measure on omega. The kernel K is defined on omega cos omega. F in the integral is generally nonlinear and is a real value function defined on omega cos R. H is usually is a given function, which is also defined on omega. And U is the unknown function defined on omega. Why talking about Hammerstein equation, what makes it to be very important? Equation of Hammerstein type are of much interest to a wide audience due to the fact that they cover a large variety of areas. Take, for instance, wherever mathematical problem is involved, I can say that equation of Hammerstein type is applicable. Wherever mathematical modeling is involved, equation of Hammerstein, integral equation of Hammerstein type is applicable there. That is, it is very important and it covers a wide area and is of much interest to a wide audience. Also, several problems that arise in differential equation can be transformed into integral equation of Hammerstein type. And in some cases, it is easier to deal with several classical problems in differential equation using the integral form than directly with differential equations. Moreover, this Hammerstein equation also play a crucial role in theory of optimization, optimal control system, and automation and network theory. The objective of this study are to study integral equations of Hammerstein type with monotone type mappings, to find suitable conditions for a proposed algorithm for nonlinear integral equation of Hammerstein type, and to obtain a strong convergence result for nonlinear integral equation of Hammerstein type, and to demonstrate, the fourth one is to demonstrate the application of the results to problems arising in physical system. Let's talk about duality mapping, because we shall be making use of it in this study. A continuous, strictly increasing function nu, which is such that phi of t goes to infinity as t goes to infinity, and phi of 0 is nu of 0 is equal to 0. For t in 0 infinity is called a gauge function. Associated with the gauge function is a mapping J E nu, which is this, and it is called duality mapping, and it is defined as this. The duality mapping is defined as this, where in this place, where this represent the duality pairing, and E throughout this presentation shall denote a Banach space. Sorry for typographical error here. This is Banach space. For P greater than 1, let nu of T be defined as this. JE in this presentation shall denote generalized duality mapping, and it is defined as this. For P is equal to 2, JE2 shall be called normalized duality mapping. Duality mapping has some essential properties, which it is important for us to quickly run through them. Recall that it is said that it represents a Banach space. If E is smooth if and only if the generalized duality mapping is single valued. And if the Banach space is reflective, if E is reflective, then that the generalized duality mapping is onto. And if E has uniform Gattuni differentiable norm, then JE is normed to weak star uniformly continuous unbounded sets. E is uniformly smooth if and only if the generalized duality mapping is single valued and uniformly continuous on any bounded subset of E. And if E is strictly convex, then the generalized duality mapping JE is 1-to-1. And if E and E star, where in this place E star denotes the dual of E. If E and E star are strictly convex and reflexive, then JE star is also a generalized duality mapping. But in this case, it is generalized duality mapping from E star to E. You recall that the general duality mapping is defined from E to E star. But in this case now, J E star is defined from E star to E. And it is indeed the inverse of J E. If E is uniformly smooth and uniformly convex, J E star is uniformly continuous on any bounded subset of E star. And lastly, if E and E star are strictly convex and reflexive, then for all X in E and for all F in E star, the equality this holds. That shows that J E star is simply the identity, is simply the identity map. And J E, that is the identity in E star. And J E star, J E is the identity in E. That is, those are the essential properties of duality mapping that we shall be referring to in this study. Monotone mapping, as it has been said, that we will be considering nonlinear integral equation of Hammerstein type with monotone mappings. Let's look at what a monotone mapping is. Let it be a Banach space with dual E star, and A be a mapping from E to E star. In this place, throughout this presentation, we shall assume that A is defined for all U in E. A is said to be monotone if for every U phi in E, we have this equality, U star minus P star. That is, the duality pairing of U star minus P star and U minus phi is greater than or equal to 0 for every U star in AU and P star in A phi. And in this situation, if A is a single valued mapping, the definition is simply the duality pairing of AU minus A phi, comma, U minus phi is greater than or equal to 0. That's for single value mapping. This monotone mapping, let's give concrete examples of them in real life. Every non-decreasing function on R is monotone. And similarly, every non-increasing function on R is also monotone. Given A to be this and X bar to be this, consider the function G from R2 to R2 defined by G of X bar is equal to this. Then this G defined by this is also monotone. Given a Hilbert space H and with the identity I in H, and given a mapping T, which is not expansive, we call the definition of non-expansive. That shows that the norm of Tx minus Ty is less than or equal to the norm of X minus Y for every X in H. Then that the operator I minus T is monotone. And the duality mapping that we have also talked about is also an example of monotone map. And let there be a convex and proper function. The sub-differential of F defined as this is also monotone. These are the examples of monotone map. Let's look at some of the existing results on nonlinear integral equation of Hammerstein type with monotone mapping. Solution of the equation AU is equal to 0, where A from E to E star is of monotone type, has been a subject of interest and studied widely. These are some of the references that consider these are some of the recent studies on this topic. And also, looking at the literature, it is observed that strong results were obtained for nonlinear Hammerstein equation under the assumption of existence of a real constant whose calculation is unclear. That is, most of the results in the literature, they have been obtained under the assumption that there exists a real constant. This real constant, how it is being obtained, it is not clear, it is not explained. And also, the literature also confirms that some of the existing results on this topic have been obtained so far in Hilbert spaces. And looking at Hilbert space and what makes some people to to be interested and find it suitable to be working in Hilbert spaces is due to some of the nice geometric structures which Hilbert spaces possess, which are not present in other spaces such as Banach space. An example is existence of inner product. It is only in Hilbert space that you can find the inner product. When we come to the Banach space, there's nothing like inner product. The closest form to it is the duality pairing. Also, in Hilbert space, there's what we call the proximity map. And also these two identities, that is identity, the third and the fourth one, that is norm of x plus y squared, which is defined as this. And for x, y in H, and ladder is 0, 1, these two identities only hold in Hilbert spaces. They don't exist in other spaces. These are some of the nice geometric properties which the Hilbert spaces possess, and which makes some results that are posed in them to be easily handled. That is, make it easier to be handled than when they are being considered in other spaces. The contribution of this study to the knowledge will be to consider the nonlinear integral equation of Hammerstein type with monotone type mappings in Banach spaces, not in Hilbert spaces. And we shall also introduce techniques which does not require the assumption of existence of real constant whose calculation is unclear. The technique, our own technique, is based on our own technique does not involve the assumption of any real constant, which no one can explain how it is being calculated. And this study will also establish the strong convergence results for nonlinear integral equation of Hammerstein type with monotone type mappings. Real value functions. Let it be a real Banach space with dual Easter. J2, as it has been said, denote the normalized duality mapping. Aber in 1996 introduced this real value function, which is phi of xy, which is defined as this for xy in E. That's equation 4.1, was introduced by Aber in 1996. Then for a smooth Banach space E and with P Q greater than 1, so that this condition holds, we introduce this map phi P, which is defined as this. Phi P is defined as this, where J in this case, our JE is the generalized duality mapping, but J in the definition of the Aber is normalized duality mapping. That shows the extension of this map, that is generalization of this definition over that of the Aber, which was introduced in 1996. Moreover, comparing the two definitions, we can see that when P is equal to 2, the definition of Aber is obtained. That is, it's obtained as a corollary for this definition. Also, let X be E cos E star. We also define the map wedge P of X into R, which is defined as this for X1, X2 in X. Strongly monotone. We have talked about monotone mapping, but in this case, in this study, we shall be talking about we shall be using strongly monotone. Let it be a uniformly smooth and uniformly complex Banach space. A from E to E star is said to be PK strongly monotone if the duality pairing of X minus Y and AX minus AY is greater than or equals to K non P of X minus Y. Observe that looking at this, that is for K greater than or equal to 0. For K greater than 0, that is for strongly monotone, PK strongly monotone. Observe that if K is equal to 0, then we obtain a monotone mapping. That shows that this class of monotone mapping, which we are considering and which we are using in this study, is more general than monotone mapping, because it is monotone mapping is obtained when k is equal to 0, and this is defined for k greater than or equal to 0. Now suppose f is from E to E star and k is from E star to E, such that the domain of k is equal to the range of E, which is E star. And also suppose f and k are p eta 1 strongly monotone and p eta 2 strongly monotone respectively, where p is greater than 1, eta 1 and eta 2 are in 1, infinity. Then we let x be E cos E star with norm x defined with the norm of x defined as this. Then we define a map A from x to x star by this. This is our map A. We define our map A to be this, and we show that this map which we define is P eta strongly monotone mapping. This is the sketch of the proof to show that this A is P eta strongly monotone mapping. By definition of strongly monotone mapping, we should have x1 minus x2, that is the duality pairing of x1 minus x2, comma ax1 minus x2, which is defined as this, which is greater than or equals to this, which is also greater than or equals to this, which is equals to this by the norm of x. Therefore, that shows that A is P eta strongly monotone. We want to talk about compact map. Let x and y be topological spaces, and A be defined from x to y, be a mapping. We call this definition of A to be, that is the definition of continuity. A is said to be continuous if for every x not in x, and for every phi in this, for every phi is equal to this, there exists u which is equal to this, such that this is subset of phi. Now we prove this because we need it in our result. We say that let A be a mapping from B into R, where B is a compact subset of E. Then there exists the subset of R so that AX is less than T for all X in P. What this lemma is simply saying is that the continuous mapping A on a compact subset of E is bounded. The continuous mapping A, that is, the continuous mapping A on compact subset of E is bounded. That is, this lemma, we also establish it that it holds. Each condition. Let E be a uniformly smooth and uniformly complex Banach space, and let P is equal to be greater than 1, eta 1 and eta 2, they are this, and also the domain of K and range of F, they coincide, which is equal to E star. And for T1, T2 greater than 0, we suppose that F is continuous, is P eta 1 strongly monotone, so that the range of F is JE plus T1F is all of E star. And also say, suppose K is defined from E star is to E is continuous, P eta 2 strongly monotone, so that the range of this is all of E. Then we prove this, we prove this lemma. That is, let A be a map defined from X into X star, which is defined by this. We will call that this A, it has been shown that it is P eta strongly monotone. That is, A is defined for this, A is defined by this for every X, which is U comma P in X, and A is continuous P. We show that A is continuous P eta strongly monotone, so that the range of A is all of X star for T, for some T greater than 0, where this lemma is also, we also establish this lemma. Coming back to transformation of Hammerstein equation, since our talk based on nonlinear integral equation of Hammerstein type with monotone mapping, we've talked about monotone mapping. Now let's come back to Hammerstein equation, the transformation of Hammerstein equation. A nonlinear integral equation of Hammerstein type on omega is given as this, which has been stated before. If we define the operator K to be this, operator K from this, we define the operator K to be this, and we define the mystic operator F associated with F to be this. This integral equation 4.2 can be put in functional equation form as 4-point theory. That is, this is the functional form of integral equation of Hammerstein type. This is the integral form, while this is the functional form of it, which is obtained with this transformation K and F. This gives us this functional form of Hammerstein equation, where without loss of generality, we've assumed that without loss of generality, we have assumed that we have taken H to be equal to 0. However, for H different not equal to 0, this is what we are going to have, which implies that this which implies that U minus H is equal to this, which is equal to this, where our omega in this space is equal to U minus H. Thus, this equation can be written as omega plus K F bar omega is equal to 0, where F bar omega is equal to this. Looking at this equation and the previous one, where we took H to be equal to 0, we can say that they are of the same form. That's why we said initially that without loss of generality, we can simply assume that we can simply take H to be equal to 0. Now suppose U, that is this Hammerstein equation in abstract form, has a solution in E. Then U star is a solution of this Hammerstein equation, where in this case, that shows that phi star will be equal to F of U star, and X star is simply U star comma phi star, because we call that our X is simply E cos E star. Therefore, X star will simply be U star comma phi star, where in this case we are going to have our U star. This U star, which is the solution of this Hammerstein equation, is simply minus K phi star. Let's now look at the convergence result. Having transformed the nonlinear integral equation of Hammerstein equation, having transformed it from integral form to abstract form, let's now establish the convergence result. We let this lambda and omega be sequences, that is, they are real sequences in 0, 1, and they satisfy these conditions 1 to 3. And our E is uniformly smooth and uniformly convex-free Banach space, and P is greater than 1, omega 1 and omega 2 are in so infinity. T1 and T2 are greater than 0, and the domain of K and the range of F, they coincide, which is equal to E star. And we suppose that F is continuous P eta 1 strongly monotone, so that the range of it is all of this. The range of this one is all of E star. And we also say, suppose K is continuous P eta strongly monotone, so that the range of it is all of E. We call that J is our duality pairing from E to E star, and J E star, it is also the generalized duality map. It's also the generalized duality map from E star to E. Both of them are generalized duality mapping. These are the conditions for our space. Now we establish this theorem that suppose this Hammerstein equation, this abstract form of Hammerstein equation, has solution in E, and N is the sequence. It is, yes, let N be in N. I will define UN and Pn alternatively by this. Then we establish that UN converges strongly to the solution of Hammerstein equation. For that result that we obtained, we established this corollary. As it has been said before, that Banach space is more general than the Hilbert spaces. So the result which we obtain in the general Banach space, we have its corollary in Hilbert space. Given the Hilbert space H and the range of F in this case, and that of the K are given by this and this respectively. Then we define the sequences UN and Pn by this. Then suppose that this has a solution in E. Then we establish that this sequence UN converges strongly to the solution of the Hammerstein equation. Let's now look at the application of this Hammerstein equation. Give a a classical example for this application of Hammerstein equation. Consider the first oscillations of finite amplitude of a pendulum whose model is given by inhomogeneous differential equation, equation 5.1. This is the equation for oscillation of a finite amplitude of a pendulum. This is the model given by, this model can be found in this text. In this equation 5.1, the derivative for z of t is periodic and odd. And phi of t is the amplitude of the oscillation, and it is the solution of this problem. The constant A, it depends on the length of the pendulum and also on the gravity. For us to transform that differential equation into nonlinear integral equation of Hammerstein type, we need what is called Green function. Green function is simply a homogeneous solution of differential equation. As an example, elliptic boundary value problem whose linear parts admit Green function can be transformed into a nonlinear integral equation of Hammerstein type. While talking about elliptic boundary value problem, simply they are a class of problems which are typically associated with steady state behavior, which are, that is, they are associated only with the steady state behavior. They are independent of the time. Solving such differential equation is equivalent to solving corresponding Hammerstein equation. And oscillation of finite amplitude of a pendulum is given as an example. For that differential equation, which is the model for the finite for the pendulum that we are talking about, this is the Green function that we obtained for it. And from this Green function, that has been obtained, that given boundary value problem is equivalent to this equation 5.2. And taking this to be equal to G of t and phi of t plus G of t, define it to be equal to U of t, then d 5.2 can be written as this. This equation 5.2 is simply homogeneous integral equation of Hammerstein type. And let's give numerical example of what we have been talking. Numerical example for what we have been talking about. Given let it be R2, and with the usual norm, if it's equal to R2, simply the dual of E will also be R2. And let F be given as this, and K be given as this. We are given U bar to be this, and phi bar to be this. Fu is simply this, and our K phi is this. From this, we obtain that F, that is the duality pairing of Fu bar and Fu bar and U bar, is greater than or equal to 7 norm 2 of U bar. And also the duality pairing of K phi bar, phi bar is also greater than or equal to 3 norm 2 of phi bar. And for this, for P is equal to 2, that shows that F is P eta strongly monotone mapping, and K is also a P eta 2 strongly monotone mapping with eta 1 is equal to 7 and eta 2 is equal to 3. These are the sample of strongly monotone mapping which we are talking about in this study. And for the sequences, that's a condition that we specify for the theorem that is stated. These are the sample of Lewis sequences that satisfy those given those stated conditions. For our sequences, we use MATLAB to verify the convergence result, and we obtain these graphs. That is, we use from different initial points, we obtain this graph. For the first one, this is the initial point. That's one when U is 1,1 and phi is 1,1, we obtain this. But that is for different initial points. This is the graph that we obtain for our sequences U and phi. In conclusion, in this study, algorithm for nonlinear integral equation of Hammerstein type with monotone mapping have been considered. And strong convergence of sequences of iteration is obtained without the assumption of existence of a real constant whose calculation is unclear. We can also see from this study that the efficacy of the technique is also displayed on how some result in Hilbert space can be extended to a general Banach space. And we have made effort also to convince the listeners about the application of the results in solving some real-life problem, which is common in physical science. Specific example for monotone type mappings and for Lewis sequences, which satisfy the stated conditions in the given theorem have also been given. These results, these results which we have presented in this study have been accepted for publication in this journal, Communication in Nonlinear Analysis. And the co-authors for this paper are Tako, SC, and Moyo. Both of them are also from Dover University of Technology. Thanks for the financial support from the CoE-MaSS for the postdoctoral fellowship, which have supported this study. These are some of the references which we have consulted. Thank you.
Thank you so much for the great presentations. We'll just open the floor. If anyone has a question.
Thank you, Dr. Mathew, for this wonderful presentation. I want to ask, can we take this, can we solve this Hammerstein equation in the nonlinear setting? Maybe the metric space, the Hadamard space, or Hadamard manifold. Can we have a way of solving the Hammerstein type equation in there?
Yeah, let me say yes. However, this study that we have considered is considered in Banach space. Most of the existing results have been in Hilbert spaces. And when we look at the literature, we decided to make contribution by generalizing the existing results to general Banach spaces. This is your question. I can say it's a further, let me say it's a further research that can this result be generalized to other spaces? That is a question that I can say, let's throw it open and let's make it to be a subject of discussion or a research to be considered. That is a further research to be considered. That this result that has been presented, can it be obtained in other spaces, such as in Hadamard spaces that you have stated, and other spaces as well? Can it be generalized to those spaces? Let's make it an open question.
I don't have much questions, but I'm just curious because I really want to understand the problem of unclear. So Dr. Aibinu, he said that when in the literature they work in the Hilbert space, it was unclear how they choose the coefficients. Now, what do you mean by being unclear? We're not able to justify the steps, or they simply refuse to explain what they have done? What do you mean by being unclear?
Okay, thank you. Let me give further information on that. Fine. This is the statement of our theorem. That suppose this is Hammerstein equation and our sequences U and phi are defined as this. And we say that these sequences will show that it converges strongly to the solution of this Hammerstein equation. Going into the literature, some of the theorem was stated that by some of the wordings of the theorem goes by saying there exists a constant. They may say there exists a constant such that this sequence converges. There exists a constant, but this constant, there's never been a way in which they explain it, how it is being obtained. Nobody explanation was not given on how it is being explained. The statement just go by saying there exists a constant. They may say there exists a constant such that this sequence converges to the solution of this Hammerstein equation. But in our results, we use a technique which does not make use of such kind of assumption.
Yes, yeah, I understand perfectly. So my question was that were they not able to prove the theorem? Because when they state a theorem, there exists a constant such that we have a strong convergence. Do they prove that theorem? Because to prove the theorem, they need also to show at least the existence. You understand that it's an abstract problem, but did they not prove the theorem, or the proof was not clear? I want to understand the statement of unclear calculation. What was unclear? Was it the proof, or what was unclear? Or did you go through the proof?
The constant which they stated, which they stated exists. Right from the statement of the theory, it was not proved how it was obtained from the right from the beginning. Right? It was not, the explanation they gave on it was not clear.
Okay, understand perfectly. And also, I have a last question. If you go to after this theorem to the next slide, yeah, because the theorem, your work was on Banach space, and now you have a corollary on Hilbert space. Yes. So you have a result on Hilbert space that overcome also the challenge of the constant. Can you please say more about these results in the Hilbert space?
Thank you. For it is generally known that Banach space is more general than the Hilbert space. And if compare the two algorithms, in this algorithm we have JE and JE star. And when we come to the Hilbert space, we know that what we have there is the identity map instead of duality mapping. Oh. And that is what makes the form of the two sequences to be different. That is, the form of the sequences in this corollary to be a bit different and even look more cozy than the one in Banach space. And so, obviously, if the result is true in general Banach space, since Banach space is more general than the Hilbert space, all the conditions that we also stated for the sequences, if they are satisfied, then these sequences can also be established that it can also be established that the sequence UN converges strongly to the solution of this Hammerstein equation.
Okay, thank you so much. Yeah, I think it is now clear. Thank you. Any questions or comments for the last time? Okay, there is no question and comments. We once again thanks Mathew for the wonderful presentations. Thank you once again.